Hello students, today we will start a new chapter that is torsion. Torsion actually is one type of loading. We already have discussed about various type of loading such as direct forces, direct stresses, or shear stresses, or even moments in our uh, finding out the shear force and bending moment of a particular beam. In that case also we have discussed about applied moment. But what if a couple or a moment is applied with respect to the axis of the member? So for this particular member, this will be the axis, right? This nib of this pen will be the axis, and if we apply couple one moment with respect to this axis, right? If we apply this moment, what will happen? It will twist the pen, right? If this end is fixed and in this end we are applying one moment with respect to this axis, it will twist the pen. This type of couple or this type of force which actually twist a member, that type of force is called torsion. So basically torsion refers to the twisting of a structural member when it is loaded by couple that produce rotation about its longitudinal axis, right? So suppose this is a shaft, and now we will be applying some couples, right? Suppose we are applying one couple over there at the end of the shaft. Suppose we are applying a force which is having some distance, right? And we are applying another load over there, another couple over there, uh, which is rotating this shaft, in this direction, right? Suppose the force is in this direction, and obviously this force is also having some distance, this distance. Suppose this force is p1, and this distance between two forces is d1, and in this case we are having suppose p2 force and p2 force and having a distance of d2. So we can say if this end is fixed of the shaft, then we can say we are applying two couples which is rotating the shaft. This couple is rotating the shaft anti-clockwise direction, and this couple is rotating the shaft in clockwise direction. So those are the forces or couples which are rotating uh, the shaft. Those couples will be called the torsions, the torque, right? Those couples will be called a torque or twisting moment, or we can say twisting couples, right? So the couples that produces twisting of a structural member are called either torque, it can be called torque, or twisting moments or twisting couples, right? Now this can be represented by this diagram also. We can represent the forces like this also, or we can represent that with two different process, like this and this, right? That means we are indicating by a curved arrow, where T1 is nothing but the couple. That means T1 is equals to P1 multiplied by D1, and T2 is equals to P2 multiplied by D2, the force into distance, right? So this is the couple, and this one is a couple. So T1 and T2 are the couples. We can represent it by curved line, or we can represent it by the double-headed arrow, right? With the double-headed arrow. So this will be T1 and this will be T2, right? So this we can indicate with the double-headed arrow using the right hand rule for moment vectors. Right hand rule for moment vectors is what is suppose for this moment, suppose if we indicate this with the right hand, then it will we can say this is giving the anti-clockwise moment. So if we indicate with the right hand angle like this, so this is indicating the anti-clockwise movement, and our thumb is in this direction, so our moment vector will be indicating this direction, right? And if we do in clockwise direction with the same right hand, we can indicate like this, so this will be giving you the clockwise movement, and this thumb will be indicating this direction, so we can say this will be in this direction. So we can represent this with this thing also, right? Now we will discuss some assumptions. So first assumption will be the material of the shaft is uniform throughout. That means the material is uniform, that means this is homogeneous, right? And the second one is the twist along the shaft is uniform. That means if you apply a twist at the end and this end is fixed, or otherwise same amount of couple you are applying, if in the application, in the process of application, this one couple, the distribution will be uniform, right? Right, so throughout the body, the twist will be same. This is the second assumption. Third one is they are saying that normal cross section of the shaft. That means if you cut any section normally, so normal cross section of the shaft which were plane and circular before twisting, this will remain plane and circular after twisting, right? So if you cut a section before and after twisting, this cross section will be plane and circular. Number 4, they are saying that all diameter of the normal cross section which were straight before twisting will be straight after twisting, and the magnitude will be same. So the radius or the diameter of any cross section will be unchanged before and after twisting, and the diameters will be straight, right? Now look at the theory of pure torsion. Suppose we are having a shaft which is fixed at one end, and other one end is applied with the torque, right? So suppose the torque is T, and the length of this shaft is L, right? And due to this torque, this plane AB, this point B is deformed now with a new point in a new point C, right? So basically, due to this torque, this B point is shifted to C, right? So this AB line now became AC, and OB now became OC, right? That means obviously this initial and final line will be having some angle. Suppose we are uh, getting this angle as phi in longitudinal direction, and this angle we are getting theta in the cross sectional direction. Now let us find some relation between them. Now, whenever you are applying this torque in this portion, and whenever this point is rotating and this point is fixed, that means from here to here, all the cross sections having some shear stresses, right, with respect to each other. All the cross, if you look at this section, and if you just cut the immediate left hand side cross section of this last end, you will be getting some shear stresses between those two planes, right? Likewise, all the planes are having some kind of shear stresses. Now, if you consider this angle BAC, in this angle BAC, from this angle we can say, from this triangle we can say angle BAC is equals to phi, right? We are getting that. Now this phi will be nothing but the shear strain, right? This is basically nothing but shear strain, right? Now what will be the value of BC? If this is L, if this is phi, the value of BC from this triangle we can say, if phi is pretty small we can say L phi, if phi is small then we can say BC equals to L phi. From this we can get phi is equals to BC by L, right? Up to this clear? Okay. Now suppose tau is the shear stress at the outermost layer. Suppose this tau is the shear stress of outermost layer. That means at this layer the shear stress is tau. Then what we can say, the shear stress is equals to the shear strain, which is phi, multiplied by the modulus of rigidity, right? So C is the modulus of rigidity, right? So we can say this, but phi we have already found out. Phi value is this. So if we replace this value phi, so we will be getting tau is equals to BC by L into C, right? Now from this triangle, BOC, from this triangle BOC, we can get, from BOC we can get BC is equals to, if theta, if theta is small, we can say the arc BC and the straight line BC is almost same, so we can say BC is equals to R theta. So if we consider this BC as arc, so this will be R into theta, where R is the radius, right? R is the radius, right? So we can say this BC is equals to this, right? So if you replace this value, what we will be getting, we will be getting tau is equals to R theta by L into C, right? From this we can say that tau by R is equals to C theta by L, right? So this is one relation between tau, the shear stress at the extreme uh, layer, right, and modulus of rigidity, and the radius of the shaft and the length of the shaft and the uh, twisting angle, right? So this is the relation. Suppose if you consider this solid shaft is a combination of plenty of hollow shaft, and suppose you are finding out the relation, this relation for a particular shaft which is having a distance of x, right, from the center, then what will be the relation? And suppose at this layer obviously the shear stress will not be the same. The shear stress at the extreme end was tau, right, at the extreme end, but at this layer suppose this shear stress is not tau, is suppose tau x, then similarly you can find out the same relation. That means you will be getting this relation tau by r is equals to tau x by x, where tau x is the shear stress at that particular fiber. A particular fiber means which fiber, which is situated x distance apart from the center. So x is that, and c, this will be equals to c theta by l, right? So you will be getting this relation. So this is the relation. This is our class for now. I will be discussing many other things later. Thank you.